If you have ever created a knowledge graph, you may have used mapping languages. Mapping languages allows you to declaratively describe how to generate a knowledge graph. However, can you truly describe your whole generation workflow in a mapping language without any pre- or post-processing? To answer that question, we need to go back to where it all started, namely hard-coded scripts. In the early days, knowledge graphs were generated using hard-coded scripts tailored towards a specific use case. The script retrieved the data from various data sources, transformed the data, and transformed it then in a knowledge graph. However, each time the use case was changed, a new set of scripts was necessary. And that's really unsustainable, as you cannot reuse these scripts in other use cases. To address this, several approaches emerged, and they are focusing on using rules. In the rules, the transformation of the schema is defined to generate your knowledge graph. These rules are adapted for each use case, and the schema transformation part is then reused in each use case. However, this approach assumes that the data is already perfect. And that's not the case in reality. In reality, you need to transform data and pre-process it in order to access it and have it in the format that you need. Therefore, it becomes unsustainable again, as these same hard-coded scripts are now used to perform the data transformation instead of generating the knowledge graph itself. To overcome this, another set of rules were added, namely transform rules and source access descriptions. These source access descriptions allows you to directly access several data sources during the transformation, as a source access describes the several properties you need to access it. However, these descriptions do not contain web APIs or streams as a possible data source. If you want to access a web API or stream, you need to use a pre-processing script that transforms the web API into a format that your source access description understands. Moreover, post-processing is needed if you want to export your knowledge graph to multiple targets, such as a Sparkle endpoint, a file, or a web API, as each processor that performs this transformation specifies the export using hard-coded scripts or configurations. That's again unsustainable, right? As you need to have these hard-coded scripts for accessing the web API or for exporting your knowledge graph. So what we propose is that we also introduce a new source access description to access the web API or stream directly without any pre-processing. Moreover, we also take the same idea of a source access description to access our targets using a target access. This way, you can directly export your knowledge graph to various targets, such as a Sparkle endpoint, a file, and so on. Everything described in the mapping rules. And that's what we propose in this paper. I'm Dylan Van Assche from IDLab, Ghent University, and in this paper, leveraging Web of Things recommendations for generating knowledge graphs, we improve the workflow of knowledge graph generation by reusing existing W3C recommendations for accessing web APIs and streams, and introduce descriptions to export your generated knowledge graph to one or multiple targets. Everything described in rules that allows you to have a reproducible workflow. across any implementation or processor. We validated our approach in two use cases, Essence and Daiquiri. In the Essence use case, we had to do smart city storytelling. And in order to achieve that, we generated RDF from web APIs of smart city sensors and exported these RDF to multiple targets, such as a web API, such as a Sparkle endpoint, and a local file. In the Daiquiri use case, we have to analyze health data sensors from athletes. These sensors are providing their data using an MQTT data stream. And also here, we needed to export it to multiple targets, such as a local file or a Sparkle endpoint. So first thing we are going to look at is what is mapping languages, what is RML and FNO, and how does it fit all together in our previous diagram. So once we know what our mapping languages and RML and so on are, we can focus on our first contribution, namely integrating W3C Web of Things with RML to access web APIs and streams. Afterwards, we can look at our second contribution, namely extending RML with logical target to export our knowledge graph to one or multiple targets. First things first, what are mapping languages, RML and FNO? Mapping languages are a declarative description for generating knowledge graphs. They define how data are transformed into knowledge graphs, such as the Resource Description Framework, or RDF. Mapping languages are reusable and independent, as the same set of mapping rules can be used in different processors and to generate the same knowledge graph. Several mapping languages exist, but we will demonstrate our approach with the Rdf mapping language. We chose to use the Rdf mapping language because it not only performs a schema transformation using RML mapping rules, but also the data transformation using FNO. But what is now the Rdf mapping language? Well, the Rdf mapping language is a mapping language based on R2RML. R2RML is a W3C recommendation that allows you to transform relational databases into knowledge graphs, such as RDF. RML broadens the scope of it by focusing on heterogeneous data. So in short, RML describes how heterogeneous data are transformed into RDF. Processors such as the RML mapper and the RML streamer, they execute the RML mapping rules to generate your RDF. The function ontology, or FNO, describes the data transformations. The function ontology FNO describes semantically and how functions without depending on the implementation. FNO is aligned with RML that allows you to describe the data transformations as well in the mapping rules. So if we look at our diagram from before, we can now replace the schema transformation and the data transformation by an RML plus FNO processor. Such a processor uses RML and FNO rules to perform the transformation from heterogeneous data into a RDF knowledge graph. But as you can see, there are still two problems left, namely the web API requires still pre-processing and there's still a post-processing script to export the generated knowledge graph to various targets. And these 2 points is what we are going to focus on now. Our first contribution is integrating W3C Web of Things with RML and focuses on the top part of our diagram to avoid the pre-processing of web APIs when accessing it using an RML and FNO processor. So W3C Web of Things avoids the pre-processing for accessing web APIs and streams by providing a set of W3C recommendations for accessing, securing, and deploying of Internet of Things. Our approach uses a subset of these recommendations to describe access and security of these web APIs and streams. We used 3 recommendations. The first one is the thing description that specifies the access to web APIs and streams. It describes the location of the web API, the kind of content you retrieve, and so on. The second is the security. This recommendation specifies the authentication and security flows when accessing this web API or stream. This way, processors know how to access and authenticate against the web API or stream in order to get the data. The third recommendation is the binding templates. The binding templates allows us to extend the 2 previous recommendations with protocol-specific descriptions. So now that we know what is Web of Things, we can use it in our processor to access web APIs and streams. And that's what's happening here. Mapping languages, processors can directly access web APIs and streams using Web of Things access descriptions. The Web of Things access description describes a stream or the web API, and the RML mapping rules transform the retrieved data from these web APIs or streams into RDF. We validated our RML with Web of Things in 2 use cases, with the RML mapper and the RML streamer. The first use case is Essence, where we access an HTTP web API with authentication. In the second use case, we access an MQTT data stream. In the Essence use case, we accessed the Smart City web API to retrieve the data from the Smart City sensors. As this web API required an authentication token, we described this with a Web of Things security description that allows us to describe to processors how the token must be placed when doing a request. The thing description, on the other hand, describes where the web API is located and the content we retrieve. Once we describe that, the RML mapping rules can use this access description for transforming the web API's data into RDF using the RML mapper. In the Daiquiri use case, we didn't have to access a web API, but an MQTT stream. Thanks to the flexibility of Web of Things, we can not only describe a web API, but also an MQTT stream, using the same thing description. Once we described the access to the MQTT data stream, the RML mapping rules can be used here again using the RML streamer to generate an RDF, knowledge graph. So now that we know what Web of Things is, how it's aligned with RML and can be used to generate data from web APIs and streams, we can look at our second contribution, namely extending RML with logical target. Logical target focuses on the bottom part of our diagram, namely the post-processing script, which we want to remove to declare it in the rules as well. So logical target is a declarative description to export knowledge graphs to various targets. Logical target specifies the export location to where the knowledge graph must be exported, which is here an external access description that can be any access description, even a Web of Things access description. It also specifies the serialization using W3C namespace formats to declaratively describe the format you want of your knowledge graph, and a compression you can optionally specify the compression to save disk space when exporting your knowledge graph to a file, for example. We can put this in practice where we export a knowledge graph to a local file with NQuats as serialization and gzip compression. The target uses a void dataset as target location. This allows us to specify an RDF dump to a local file or anywhere else. The RMLT serialization has a format NQuats that specifies NQuats as export format. And we also have a compression that says we have a compression in gzip. This way, a processor knows that every triple that needs to be directed to this logical target, that needs to be dumped to a file with NQuats as serialization and gzip compression. But speaking of processors, how do they know which triple needs to go to which target? That's what we accomplished with RML logical target property. We aligned logical target with RML through the RML logical target property, which is situated in the RML term map. This allows us to export knowledge graphs on RDF term level for fine-grained control. So each term of a RDF triple can be directed to a different target. Moreover, we can export it to one or multiple targets at the same time by defining multiple logical target properties across multiple RML term maps. So in general, all generated triples from a specific RML term map are exported to a specific logical target. So on the left, you have the various data sources. On the top, you have the RML mapping rules and the logical target rules, which are used by the RML and logical target processor. This processor will first access the data from the various sources, transform it into a knowledge graph, and then use the logical target rules to export its knowledge graph to various targets, such as RDF, JSON-LT, Sparkle endpoints, and so on. So if you put this in practice, we have here two triples, namely one with predicate FOF name and one with predicate schema name. In the first RML term map, we define a predicate FOF name and define a logical target as a Sparkle endpoint. So each triple using FOF name will be exported to the Sparkle endpoint. In another term map, we define the predicate schema name. So each triple with schema name as predicate will then be exported to the target there, which is a local file. This way, we have fine-grained control over where each triple is exported to. So you can not only export a whole knowledge graph, but also parts of it to a certain target. We validated logical targets in two use cases, namely Essence and Daiquiri, and implemented in the RML mapper and the RML streamer. In Essence and Daiquiri, we exported it to two targets. The first target is a local file with NQuats and gzip compression to save disk space when creating backups of our knowledge graph. The second target is a Sparkle endpoint, in which we updated our triples using Sparkle update queries. This allows our partners to directly access the Sparkle endpoint and the knowledge graph using Sparkle queries. In practice, this means that we on the left have our Essence and Daiquiri web API stream. We have then a Web of Things thing description and security to access the Essence or Web API or the MQTT stream of Daiquiri. Once we have accessed this with the RML mapper or streamer, we can use the RML mapping rules to transform these data into RDF. But then we still need to export it, and that's where the logical target rules are for. They export it to RDF and a Sparkle endpoint. The same descriptions can be reused in various use cases, which allows it to be reusable and reproducible across multiple use cases. Let's rewind. A short recap. We first looked at what is a mapping language, what is RML, what is FNO, and how does it fit all together. Once we know what a mapping language and such on is, we looked at our first contribution, namely integrating W3C Web of Things with RML to describe access to web APIs and streams directly in the mapping rules. Our last contribution, the second contribution, is extending RML with logical target, which allows us to declaratively describe how a processor should export our generated knowledge graph to one or multiple targets with fine-grained control. So in conclusion, if you integrate W3C Web of Things and logical target in your workflow, it makes your workflow reproducible across machines, as you are not depending on, as you completely describe your workflow in mapping rules. It's independent of specific processor parameters, so you're not tied to a specific processor anymore. And you can export it to multiple targets at once without having to using a post-processing script or anything else. So if you're really into knowledge graph generation and you want to make your workflow reproducible, check it out on our website, rml.io/spec/RML target, or on our GitHub, where we provide implementations of the RML mapper and RML streamer. Are there any questions? Thank you for your attention.